Good evening, everyone. I hope I am clearly audible. Sorry for the delay. My name is Tazeen, and let us start with the eighth lecture of second module of NPTEL course, Geographic Information Systems. We are talking about real world to digital world through GIS. Today's session highlights are about object relations, data quality, what are the different types of data quality, the shortcomings of these data objects, and role of maps in GIS. So this is where we stand. We are more than halfway through now, and today we will be covering up about map representations and how objects are an important part of it. So let us quickly go through previous lecture summary. So in previous lecture, we were talking about real world model and how it reduces our complexity, how we are connecting the real world to the data, which turns out to be our database, and that database is utilized in GIS. Then we also got to know some basics about objects, that is, they are nothing but carrier of information in the data models. Then we also talked about object characteristics, their types, attributes, relations, geometry, and quality. Then we spoke about data model design and graphical representation of data objects using points, lines, and polygons. We also gave a brief about object attributes. And for today's session, we are going to continue with object relationships and shortcomings of GIS models. So we will first be discussing about the assignment 6 questions. Please note that the question sequence can be different, but the questions are supposed to be the same. So please check for your order. That's what sir asked me to give you as disclaimer, because how NPTEL puts it in a different order, we are not aware of that. So please, I hope you will be able to match it. So the first question is computerized database columns in a computerized database columns are known as dash and rows are called dash. So the correct answer is B. In a computerized database, columns are called record and rows are called field. This is self-explanatory. Moving on to the next one, to protect the confidentiality of a file, dash feature is utilized. Locking, saving, encryption, none of the above. The correct answer is encryption because I'm sure you are aware of this word encryption. A lot of your, social medias like chatting apps like WhatsApp, they serve encrypted data. So what happens is that whenever any data is encrypted, it means that it is unreadable by the text editor or the utility program, that is the handler. So one can decrypt the file to read in application programs, but encrypting it makes it more secure. So your file has some sort of privacy. Third is SQL or structured query language is initially developed by Dash company. So the initial development of SQLs were by IBM's. Fourth, the key to locate data physically on the disk is called as dash indexing, hashing, both, none. So the correct answer will be hashing because a hash function is a function that is used to map data of arbitrary size. Okay, so it can be of any random size to a fixed size value. So what happens here is that this helps you to locate the data physically on the disk. So the correct answer will be hashing. Fifth, positioning and indexing in database dash storage volume. Increases, reduces, can be both, none. So positioning indexing in database can reduce your storage volume. Why? Because in a relational database, positioning data indexing, this reduces the storage of the volume. So it it will in fact also help you in reducing the redundancy of the data by removing duplication. Sixth, if geometrical and attribute data of GIS is stored in two separate databases, it's termed as dash system. Integrated, hybrid, geographic, combined. So in this case, the answer will be hybrid system because what happens that in a hybrid system, the system that stores the geometrical data and attribute data are in two separate databases. So that's why they are known as your hybrid system. The storage of attribute and geometrical data in the same database is known as your integrated system. So they are placed in one single database. Seventh, remove the odd one out from the following combinations. So your correct answer is C because the exclamation is no orthological operator here. Eighth, which among the following is a statistical operator? Addition, maxima, multiplication, both A and B. The answer here will be maxima because addition, multiplication are arithmetic operators and maxima is your statistical operation. Ninth, the process of grouping of attributes according to user needs and generating maps can be called as classification. Why? Because this process involves grouping of attributes according to the limits set by. One second, you're hardly audible. One second, let me increase. Yes. The process of grouping of attributes according to user needs. Oh, sorry. Which among the following is a statistical operator? Okay, yes. What are the other options that you have? Yeah, so average is your statistical operation. Yes. Okay, so what happens in classification? We are grouping the attributes according to the limits that is set by the user. And in reclassification, what we are doing is we are changing the attribute values without altering the geometries. So we keep the geometries fixed. So therefore, the process of grouping attributes according to user needs and generating maps is known as your classification. 10th, dash feature is used while digitizing features in GIS softwares to ensure logical consistency. Digitizer, eraser, pencil, snapping. So the correct answer here is snapping, because the snapping feature ensures new digitized lines correctly snaps to existing vertices or edges. Edges and vertices has already been explained to you in the previous class. I hope you remember. So let us talk about the outline of today's lecture. So we are talking about object relations, the quality of the data, the types of quality, then GIS map and database, shortcoming of GIS models, roles of maps in modeling. So let us start with what we understood about real world modeling. So this is just a small brush up. So what we are doing here, in a real world model, we are representing it into GIS or geographic information systems, and this is done to necessarily simplify your real world models or the physical environment into the digital world. So the primary goal of GIS here becomes to build a standardized model that accurately represents the actual world regardless of individual subjective perspectives. So when we are talking about object relations, we here are considering object relations as well as entity relations in a real world model, because they are synonymous. So such that there could be a distinction between them, we compute relations in different forms. So how are we doing it? We are doing it, let us say we have three basic ways. So the spatial positioning of an item may be determined by its coordinates, such as intersection of lines or overlapping of regions. Then there is an object structure, which is also known as the relation. We are in this encompasses several elements such as starting and ending points of a line. We have already understood what are lines. The lines that constitute a polygon. So three or more lines are making polygon, and the spatial arrangement of the polygon in respect to a line. Third, relationships that need inclusion as characteristics, such as subdivision of a taluk into townships or hierarchical tiers of non-intersecting crossing highways. So we are very distinctively trying to identify the different relations between the objects as well as the entities. So, what are the different types of object relations? The first is adjacency. So, these are some additional information that I'm sharing with you. I think that these may not be there in your Professor Bharat's presentations or lectures, but these are just additional information I'm sharing with you. These will definitely not be in your assignments related to this particular lecture, but this will help you. So when we are talking about adjacency, this describes whether features share a common boundary or not. For example, polygons representing neighboring land parcels are adjacent. So let us take this example on the right side. So let us assume that this is a network plan of a city X, and within this we are representing the outer, let's say, the boundary of the city, administrative boundary by blue, and the red ones are the different districts or maybe different wards within the city. Okay, not districts. Let's call it different wards within the city. So in this case, these two wards are representing adjacency because they are land parcels adjacent to one another. Next is containment. This relationship indicates whether one feature is completely contained within another. An example would be a building feature is contained within the boundary of a land parcel. So, for example, let us take this particular ward of the city. Here, if these two boxes represent two buildings, this is representing a containment object relationship of these two objects with the boundary of the ward. Next, we have connectivity. So this refers to the connections between features, which is especially relevant for networks like roads or utility lines. For example, road segments are connected at intersections. I hope I don't have to explain this too much. You can see lots of intersections in the entire diagram. So all of these intersections actually represent your connectivity type of object relation. Next, you have proximity. This describes how close features are to one another. It can be used to find features within a certain distance of a reference point. So, if I just consider, let us say, these two triangles as two different features, right? So I am identifying them at a distance of, let's say, 15 kilometers, right? So this 15-kilometer identifies both these features at a certain proximity. Next, we have overlap. This occurs when features share a portion of their spatial extent. For example, two polygons may partially overlap if they represent different land use types within a city block. So here we will take the overlapping of these two diagrams. One is blue and the other is green. So these are not two different land use types in a city block. Let us assume that for these two features, so let us say these two features are two metro stations, all right? So from these metro stations, we did an analysis and we found their influence zone. So these are two influence zones of the metro stations which have a proximity relationship, but their influence zones have an overlap relationship. So this area, this is a common area which is influenced by both the metro stations. Next, we have intersection. This indicates where features intersect across each other. For example, the intersections of roads in a road network. Okay, so here again you can see intersection of road network. So for major roads, it is an intersection relationship, but for all other major and minor, it is a connectivity relationship. Now let us understand the basics of object quality. The true value of any description of reality depends on the quality of all the data it contains, that is, graphics, attributes, and relations. In the initial data modeling stage, the assessment of data quality should be included. So let us consider certain attributes and try to understand from examples what are we talking about. So let us say there is an attribute called the graphical accuracy. So this graphical accuracy is measured such as plus minus 1 unit accuracy. So if whenever we are looking at graphical accuracy as the quality of the object that we have, we are considering that there will be an upgraded version or a better quality by 1 unit of that graphical accuracy. Now, for example, if I have an image, okay, so if I have a image as my graphics, if my graphics is represented by an image, so I will be measuring this 1 unit by pixels, right? So this will change as per whatever is my attribute, whatever defines my graphics. Second is updating. So when and how data should be updated. So however you are updating, yes, for so vectors are in three forms. So if it's a point, you're going to define it by the intensity of the point, okay? If it is a line, you will define it either by the length of the line or by the thickness of the line, correct? If it is a polygon, it will be defined by the area that is demarcated by. How accurately, if you are, let's say you are using your polygon vector data type to represent your building, so how accurately you have defined that particular building in the real world will define your object quality, correct? Yeah. So how you are updating, when and how data should be updated. So for example, if I take a Google map from 1991 and if I take another Google map from 2010, So, the buildings or the roads or the water bodies, the areas and their densities might change. So, if there is no updating of this data, right, when and how the data should be updated, if that is not done, that again, uh, it deteriorates the quality of your data. Next is your resolution or detailing, when roads should be represented by lines or by both road edges. Sorry, whether road should be represented by lines or by both road edges. So what this means is that sometimes in certain data sets, what happens, even if you go to OSM, I don't know if you have explored OSM yet, OpenStreetMaps, which we have discussed in like I think long back. So if you download your shape files of, let's say for example, roads, since we're talking about roads, if you download the shape file of roads from OSM, you will be seeing that there is a simple line polygon used as the vector data to represent your roads. Similarly, if you download the rivers, okay, so when you will download the rivers, you will see that there will be again lines representing your rivers. But in the same data set, there's one more vector file, shape file, which is known as your water bodies or something known as water shapes. So, like I'm not remembering the exact name, but it's either water bodies or water shapes. So if you open that file, you will see that the same river which were represented by lines now become polylines. Sorry, polygons. Why? Because the area of your water bodies are also there. Even the area of your river or the width of your river is also included. So, if you have seen the Hooghly River, which goes from the adjacent side of Kolkata, you will be able to understand that it is not enough to represent something like the Hooghly River with just a line. You actually need to represent it with a polygon to define the area correctly, right? But in the same way, if you are just, um, looking it at a different scale, okay, so let's say I am looking it at India level scale, okay, not I'm so first I was looking at it from West Bengal scale. Now I'm looking at from the entire country scale. So even when I look at it from the entire country scale, then the line feature is going to suffice my needs. But if I go to the West Bengal scale, the line feature will not suffice. So the detailing depends on the resolution, depends on the scale on which you're working, and accordingly the object quality should be defined. Extent of geographical coverage, what are the coordinate extents and bounding box properties. Now this means that from where to where you are looking at your geographical coverage, whether I am looking at only a certain edge or if I am looking it in context with something else. That will also determine your object's quality or your data's quality. Then we have logical consistency between geometry and attributes. This is very important because whatever geometry you are making, the attributes needs to be consistently updated according to your geometry. So they always work parallel. Then you have representation, discrete versus continuation. So whether your data should be represented in a discrete form or in continuous form. So this also reminds me of one of the flaws that is there in the OSM files. So let us say technically a correct GIS shape file, if I want to keep my geometry and attribute intact in the correct form and also address the logical consistency, if I am marking, let's say, Aurobindo Road, and then I am also marking Chitranjan Road, then the entire Chitranjan Road should be one line feature. Okay, that means it should be a continuous data. But if you look at the OSM file, there will be breaks. So it is a discrete form of data from OSM. So if you are doing analysis, let us say you are trying to do network analysis or you're trying to do something on space syntax that gives you the integration and the axial tendencies of your road networks, which tells you the nodes and the cluttered areas within your road network. So if you're doing some analysis like that, your results are probably going to come out wrong because each road which is named as a single node which moves in a single flow should always be a continuous data and not discrete. But if you use OSM data for this kind of analysis, it has discrete data which is like redundancy in your data. So it will give you incorrect outputs in various locations. So you have to be very careful with this also. So this also determines your object quality. Then you have relevance, where input may be surrogate for original data that are unobtainable. So, you need to have relevant data with respect to whatever analysis you are planning to do. For example, if I am doing network analysis and I have incomplete road networks or discrete road networks instead of continuous logically consistent data, then the relevance of my data is going to get lost. The objects relevant will be lost. It needs to be intact with the original data set. You have to take care that uh, whatever is your objective for the analysis that you're planning to do, your data should be relevant with respect to that. Similarly, if the same problem continues for a smaller area, okay, so if you're using OSM shape files which are ready-made for you and you're trying to perform something like network analysis, if your area is small, it's comparatively easier to make corrections. But if your area is huge, if you're working on regional scale, for example, if I want to look at the entire of South 24 Parganas, it's a huge area with almost, I think, over 9,000 square kilometers. So an area of that scale, you will probably take forever to update your shapefile. So you have to be very careful with what kind of data, what type of object, and what is the quality that it has. Next, in GIS, object quality refers to the level of accuracy, precision, and reliability associated with spatial data representing geographic features. It encompasses various aspects of data quality that are crucial for ensuring the reliability and usefulness of the information contained in a GIS dataset. So, this is just a representation of two different types of data sets, and you can see uh, so this is basically a raster file of the data set, but just with the raster file, I can tell you by looking at the raster file itself that even the Google Map quality which they have in their background is pretty crisp and precise. It is quite possible that whatever a demarcation of this vector day, so these are all vector representation of different sectors on on this city, and they have done object based PCA, so PCA is principal component analysis. So whenever you are doing something like this, and if your object data is intact, whatever lines you will be drawing, it can be quite reliable and useful piece of information. So it means that your base data set should be correct. Your base data set's quality and reliability should be most appropriate to get the correct output, as in this case. Next, we see, so we have talked about these even earlier. So let us try to understand. So in initial assessment of data quality, we include certain modeling stages, which includes your positional accuracy. So as per the position of your data set for different, let's say, for example, in all of these examples, we have considered lines. Okay, so these lines can also make your polygons, and maybe at the, so maybe this is a whole polygon, and one of the edges of the polygon, which is formed by these two lines, is showing you this dangle kind of error. So positional accuracy means that the position of your data set, uh, or the attribute setting of your data set is not in the correct position. Then it has your attribute accuracy, that means the information that is associated with these geometry, that information is not accurate. Then you have temporal accuracy, that means the accuracy of data in different timelines. Then you have logical consistency. So logical consistency, again, as we had understood here, that means the coherence or the uh, parallel relation between your geometry and attributes, that is not correct. There is some error in there. Then you have, yes, 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 yeah. Then you have data completeness. In many data sets, what happens, especially in pre-downloaded or ready-made data files that is available to you online, for example, OSM, what happens is that there are a lot of incomplete information. For example, let us say this is a road. Okay, so okay, let's not understand it here. So let's understand here. It's okay. Let's understand it here. The roads are more prominently visible to you, I guess, in the orange. So let's say this is one road, correct? This entire, okay. So what is going to happen? How you are saying that there could be incomplete data? It may be possible that this line is running through here, then this small portion is missing in your data set, and then the line continues through and through. It is also possible that the small roads or the local streets that you see, which is very lightly visible in a grid form, those lines are missing. You don't have any of the local streets. They have just marked the national highways and maybe the state highways and also your collector streets, but no local streets are present in your data set. So in that case, there will be data incomplete. So the completeness of your data is also very important. You cannot have loops or you cannot have undershoots or dangles present, because they not just represent a wrong position, but they also represent incomplete data. Additionally, overview elements are needs to be taken care of. So the purpose, usage, and lineage of your data quality should also be clear to you as a user or as a producer. Now, there are several components of object quality. We will learn about some of them which are important and which will be useful for you. So, what is spatial accuracy? This measures how well the position of features in the GIS dataset corresponds to their actual locations on the Earth's surface. High spatial accuracy means that features are represented in their correct position, right? So, if you see this, I'm sure you can see this white polygon. So this white polygon actually represents your vegetation parcel in a specific geographical location. So can you see that it is accurately marked? So this is like a kind of spatial accuracy, because your base data, the quality is so good that the chances of making errors with your attribute and geometry is comparatively low. Then you have attribute accuracy. Yeah, spatial or positional, it's the same thing. So here also you're talking position is like the literal term for it. Spatial means that spatially you're trying to pinpoint the position of your specific object or data set. Okay, so this is the same. It's the same thing. It's just what to say, a synonymous name for it. Then, yeah, then you have attribute accuracy, which we have also tried to understand in the previous slide. So here we assess the correctness and reliability of the non-spatial information. That means whatever information is associated with this particular polygon. So, for example, how accurately have we measured the perimeter of this vegetation parcel? Then how accurately we have also measured the area of this vegetation parcel? Just by drawing this line, is the line thickness sufficient to cover the vegetation parcel, or we are also overlapping a road network which is running along here? It should not be overlapped. So that also marks your attribute accuracy. So uh, whatever non-spatial data that you're going to store in your tables are going to come here, and it will ensure that the descriptive information about your feature is accurate and it is consistent. Then you have completeness. It refers to whether all the necessary features are included in the data set or not. Maybe there is a small gap here due to which the accuracy of your completeness will be hampered, and also your attribute accuracy will be hampered. because the moment I'm not able to draw the complete polygon, even though my spatial accuracy remains the same, the position of the vegetation parcel is not getting hampered by that missing small gap or line in my polygon. But what will get hampered is the polygon perimeter and the area. That means my attribute will become incorrect. Similarly, it will be an incomplete attribute, so the completeness will also not be fulfilled. Then you have your logical consistency. So here what happens, it will check if the relationship between features are as well as the attributes are associated with them are logically consistent. For example, a river cannot intersect with a lake within the same data set. That means you need to have it in the correct position, right? So these are mistakes that create your logical inconsistencies. Then you have your temporal accuracy. That means the temporal information which is associated with your timelines, uh, the date of the data collection or the last update of your data collection. Like I mentioned, if you have a data from 1991 and if you see it in 2010 and there is lack of update of your data, then there will be a temporal inaccuracy. Then you also have precision. This refers to the level of detail or granularity in the spatial representation of your features. So this will relate to how accurately your coordinates represent the actual shape and location of a feature. So for example, if you just okay, not here. Let us come back here. So if I am talking about precision, it means that the exact coordinates of this vegetation parcel should be maintained, and at the same time, the actual shape of the vegetation parcel should be maintained. So if I leave this gap here, even though the coordinates are going to be correct, but the actual shape will become incorrect. So again, the precision will fail. Next, we have scale dependency. So what happens here? The object quality can be affected by the scale at which the data is viewed, which I have already spoken about in previous slide. So in that case, what is going to happen? That some of your features may be represented differently or omitted entirely at smaller scales. So we took the example of Hooghly River when we are looking at the state level, when we are looking at West Bengal, and when we are looking at from the national scale. That is, we are looking at the entire Indian context and we are trying to see Hooghly River. So, what is going to happen? You have some canals that are coming out of Hooghly River. If any of you are not aware of it, you are requested to go to Google Map and check it out. You will see there's a circular canal, there's a Pakjala Khal, there is Kishtupu Khal. So there are various. There is um, Toli's Nala, so which is also Adi Ganga. So if you know any of them, you will understand that they are going to be visible to you as lines when you're looking at the state level scale. But the moment you go to the national scale, those canals are not going to be visible to you because even Hooghly River will be hardly visible to you in like a mesh. So the scale dependency also plays a very critical role in your object quality. Then you have your data source and acquisition method. So here we are understanding the source of the data and the method used to collect or generate it. It is essential for assessing its quality. So it may be possible that I have a data set where I have gone on site, I have measured things, and I have tried to create updated maps. But there is another person who's sitting on the desktop who is using satellite data. Maybe my satellite data was last updated in May 2024. Sorry, May 2023. But suddenly there was floods, and due to floods, the recent data which is not available online, I try to go on site and measure that data and update it. So here the acquisition method which I have used and the source of my data, it really matters a lot. Correct? Then you have metadata. We have understood metadata in a lot of previous classes. So here metadata will provide you the detailed information about source accuracy, currency, and all of other relevant characteristics of the data. It is giving you the data of your data, allowing users to make informed decisions about its suitability for specific applications. So from the metadata, you can actually find information that will help you assess whether this data is going to be useful for my analysis or assessment or not. Now we have this data model slide. I think I forgot to delete it from the previous lecture. I'm extremely sorry. So this is the correct slide. From database to GIS map. It is rare that a database has to be modified to fit a data model. So what happens that in lot of situations, we have to assess the data which is already available to us. Again, I will be taking OSM's example because initially, uh, I as a GIS user, I was heavily dependent on OSM data, but eventually I realized that using that data is good to support my uh, the basic data which I need to do my analysis. It is good to support that, but it is not very efficient to do 100% analysis of what I want to do. But it will also depend on the location. So if you look at the OSM data that is present for Kolkata, and then if you go and check out the OSM data that is present for Bangalore and Delhi, you will find that the data available for Bangalore and Delhi are much better in quality, and they are also much better in terms of updated vector files or updated attributes and features in your data set than the one which is available for Kolkata. So, in order to fit your model or in order to make the data fit for the kind of model you want to make, it is important that you modify your data sets. Like for me, I always have to modify my data sets, but these basic uh, sources of data help me get a lot of support to not overwork on just creating a data sets to do my analysis, right? So the application themselves, as well as the data model that has been meticulously developed, are what ultimately determine whether or not the GIS application in question is successful. So the issue at hand is thus more one of picking an appropriate database with respect to the following: acquisition and control. It is very important to understand how much control you have on your data set because if you don't have proper control, you will not be able to modify it according to your model fitness. The second is the structure of your data sets. The third is the storage. How much storage capacity does your geo server or your cloud service has? How much data do you need to store? Then updating and changing, managing and exporting or importing your database, processing, retrieval and presentation, analysis and combination. So what happens? All of this eventually lead to a process of transformation and combination of multiple analysis that gives you a certain outcome. So all of this, whatever issues we are talking about, it will ultimately affect your final analysis. So it is important that you go through all the stages. You make sure that from the stage 0 till stage 100 all your things are correct, but the stage 0 is most important. You will have to remember that. So be very critical about assessing the data set, the source of your database, and the accuracy of your database. So what are we trying to say when we are saying data collection and storage? So it begins with gathering relevant spatial and attribute data. We all want to do that. Nobody wants to sit and make data sets from scratch. This information is then organized and stored in a database where it can be efficiently managed and assessed. Then you have spatial database management in the form of SQLs. So here a spatial database is designed to store, query, and analyze the geographic data in hand with you, and it includes specialized tools and structures to handle spatial information such as points, lines, and polygons. So, integrating this entire database or data collection with your GIS software, what what are we doing when we are integrating it? We are storing the data. So, this data stored in your database is integrated with the GIS software, and this provides you with certain tools and capabilities to analyze, visualize the spatial information. So, what is going to happen if you don't have spatial information? For example, I have an attribute data that is spatially incorrect, but the attributes of that data is absolutely correct. In that case, what am I going to do? If I know that, okay, this is, let's say, some lake, okay, lake X. So if I have lake X and I know it is located in Chennai, correct? I know exactly at which location in Chennai it is located. I will do what? If I put that data on GIS and it is showing me in maybe Finland, what am I going to do? So there is a tool in GIS software which allows you to relocate your data set. Okay, it is a very tedious tool. It takes away a lot of energy and hard work to do that. So there are two ways of doing it. The first one is you know the exact coordinates of your shapefile or of your feature, and you change the coordinates of your shapefile manually. This is a more uh, what to say manageable way of doing it. The second method is because normally when we have just a polygon representing lake, it is really hard to locate it through its coordinates on the exact location. But what we can do it to ease our process, we will first take the coordinates, maybe we'll Google it, we will take the exact coordinates and we will change the coordinates of the polygon. Okay, so what will happen, it will not go and sit exactly on top of the correct spatial location of your lake, but it will somewhere go near it. So now what you will do is you will pick points from your from your shapefile. You will pick points. Okay, so let us say this is my lake. Okay, so if the lake actually is here on my base map, so I can see that on the satellite imagery, I can see the map is here. So the lake is here, but it has after putting the coordinates, it is showing somewhere here. So what I will do is I will pick points. I will have to very closely examine the boundary of my lake and then see, okay, these 4 points will be good reference to place this over the correct location. So I am going to mark points and I will identify the location of each the points I will be marking, and then finally when I finish those markings I will give GIS the command to shift this polygon to the reference markings that I have done, and then finally it will move to the correct position. So if you are not able to integrate it properly, if your visual spatial information is missing spatial or non-spatial data, the non-spatial data is easier to restore, but if your spatial data is missing, it's going to be very difficult and a tedious process, but it's not impossible. You can still do it by the method I have just told. Next, we have data processing and analysis. So in the GIS environment, the data undergoes various operations like spatial analysis, overlay, geoprocessing, and calculations. This step allows for deriving new information from original data sets. Then you have map design and cartography. So what happens here is the data which you have once processed and analyzed, you use that same data to create map, and this involves designing the layout. Then you will be selecting symbology or color codes for your representation. Then you will also incorporate your labels. You will label your map, you will put your legends, and then you will add other cartographic elements to effectively communicate your information. What are these cartographic elements? These cartographic elements are elements like your north point or the scale of your map. So I can show you this, but not today because it just skipped my mind that I should keep it somewhere beside here so that you can easily correlate what are cartographic elements. But I will definitely try to show you one of the maps that I have generated cartographically and designed in using GIS for effectively for this, because this is one of the most commonly used items in the entire thing that we will be doing. So I will show you the type of map I have done. Geospatial visualization, the GIS software renders the data onto a visual display, which may be a computer screen or a printed map. So this visualization allows users to interact with and interpret the spatial information. Then you have a map output. So in a map output, the final map is produced either digitally or online for viewing or for printing. This is completely user dependent. It can be electronic or it can be in a physical form. Then you have map interpretation and decision making. So what happens is that sometimes we are making master plans using your GIS. Sometimes we are making different sort of cartographic maps. We may even make a forest fire map, or we may make a flood determination map. So based on those, there are organizations and institutes that do their decision making as well. So it provides a clear representation of the geographic features and their attributes. So it gives you a very valuable information depending on the type of analysis and output you are able to generate from GIS. Now, what are the shortcomings of traditional GIS data models? So this is all theory, might get a little boring, but it will give you some piece of information where you should not be using it or how you can overcome these shortcomings. So in traditional GIS models, be it raster or vector, each of them have their own limitations. So here are some of the shortcomings that we will be discussing. There are many more, but these are the most commonly encountered limitations or shortcomings that we have. So we have limited representation of reality. It can never be 100%. We all understand that. Both raster and vector models have inherent limitations in representing complex real-world phenomena, and the raster data on itself can struggle with representing continuous or irregular features, because when you have small squares or pixels marking your boundaries, it already makes your data little irregular rather than in case of a vector file. For example, if I'm making a land use land cover map, it is going to come out as a raster data. No matter how accurately you want to make it will always have an irregularity in its feature, and it will always have some sort of redundancy associated with it, and may not represent the exact complexity of your real world. So, similarly, in case of vector data, this struggle comes when there is a continuous surface, correct? Next, we have storage and processing efficiency. What happens is that raster data can be memory intensive, especially for high resolution data sets. So if you're having something which is very high res and very crisp, you will probably have to face storage and processing challenges. In case of vector data, on the other hand, it can become complex and inefficient when dealing with large data sets or data sets with many features. So, when we are talking about the raster data, we are more concerned about the quality or the resolution of our raster data for looking at its efficiency in terms of storage. But when we are talking about vector data, it is about more number of features. So, let us say I have a raster data that is representing my water bodies, my agricultural fields, built up area, road networks, and also my forest lands, correct? And at the same time, I have exactly same files that represent the exact same area in terms of vector data. So I am representing all my agricultural fields and water bodies from polygons, then I'm using the line feature for my roads, and again the forest land and the build-up are shown using the polygons. So what happens? Vector data, because you can zoom in as much as you want, it is working on more base information. It is working on a larger data set because there are more number of features. As many lines as you have and as many polygons as you have, the storage capacity required will be more and more. So if I have the same scale of data for raster and vector, the vector is always going to demand more storage and processing efficiency. Okay, we will just take a 10 minutes break. I will be back at 7:15, and we don't have too much left. We have just a little bit more left, and then we will finish it off.
অ্যাকাউন্ট আছে ওই islam_mb@outlook.com।
আমার কাছে কোনো অ্যাক্সেস নেই। কে বানিয়েছে এটা? সাইয়ের কাছে ইয়ে নেই, উত্তর দিচ্ছে না। ফোন করে নাও, ফোন করে নাও। তুমি এখন আছো না বেরিয়ে যাবে? আচ্ছা, ঠিক আছে, তার আগে যদি শেষ হয় তাহলে কথা বলবো। না না, আমি একটু ব্রেক নিয়েছি, আমার না গলা শুকিয়ে যায় এতক্ষণ বলতে বলতে। মানে খুব টায়ার্ড ফিল করি, 40-45 মিনিট পর মনে হয় একটু ব্রেক নেওয়া, বলতে পারি না।
এইটা হলো সেটা প্র্যাকটিসের জিনিস না। এই মানে দেখতাম ওই আইপিএস এর যখন ক্লাস হতো
হ্যাঁ।
ওইগুলো তো ধরো বেশ লম্বা ক্লাসে প্রায় 2 ঘন্টার কাছাকাছি মোটামুটি 3-10 মিনিট 2 ঘন্টা। আমি তখন বলি তো মানে পরে আরো 1 সপ্তাহ কোথায় বলবো
আমার না মানে অনেকটা চেঁচাতে হয়, ওরা বলবে ম্যাম ইউ আর লেস অডিবল, প্লিজ স্পিক লাউডার, প্লিজ স্পিক লাউডার। এবার একটু চেঁচাতে হয়, প্লাস ল্যাবে বসে আমার খুব একটা কমফোর্টেবলও লাগে না যে একদম টপ অফ দ্য ভয়েস আমি চেঁচাচ্ছি। দাদা পায়, এই আগের সপ্তাহে পেয়েছি, আগের সপ্তাহে তোমার দাদা ভালো মানুষ সবার জন্য, আমাকে ছাড়া।
ঠিক আছে,
আমিও সবার জন্য ভালো মানুষ, দাদাকে ছাড়া।
ওই জন্য তো আমরা আমাদের শেয়ার নিতে
ঠিক আছে, দেখি শেষ হয়ে গেলে। আমি কিছু ভেবেছিলাম ওই জিনিসটা নিয়ে।
ব্যাকগ্রাউন্ড ব্যাকগ্রাউন্ড
না শুভেন্দু,
ও ও লেটস গো
okay, so let's continue and finish this session today. Next shortcoming that we have listed for you is generalization and scale dependency. You have already understood this, so I'm not going to stretch it too much. But in case of both raster and vector data, you will have some struggle in generalization, as simplifying these complex features will result in loss of important information. So I have also said this previously, that the moment you will change your scale, so if I have uh, raster data or even a vector data for a certain scale, so if I had the river Hooghly marked for the scale of Indian context, then the moment I change my scale to the state context, that data will be incomplete data with less precision. It will have spatial accuracy, but it will not have attribute accuracy and other forms of accuracies. I hope that part is already understood to you. Then we have limited topological information, especially in case of this raster thing, because topology information we usually do not have in vector. We have raster data sets of all these digital elevation model and contour maps, unless you are making contoured lines. So raster data lacks explicit topological relationships, which are crucial for tasks like network analysis and geometric operations. So you have limited topological information in this case. Then you have complex data integration. If you are integrating different types of data like raster and vector, it is going to be really challenging for you, because this will require complex data conversion and processing, and it is actually very tedious and hectic to get hold of both of them at the same time in the same space, and also have the precision and accuracies that you desire. It's something which is very challenging, and so far I have not been able to handle that very efficiently. Then there is difficulty handling the 3D and time-based data sets, that's your temporal data sets. So in traditional GIS models, there is a possibility of not being able to handle the 3D or temporal time-based data set as effectively as more advanced models and systems designed for these purposes. So many times these data are so heavy on your system that you might need a different a different uh, structure of your performing device that will actually help you get the outputs. Then you have difficulty with continuous surfaces. So if you are representing continuous phenomena like elevation or temperature or pollution levels, which are in continuous gradients, it is going to be challenging whether it's vector or raster, because they rely heavily on the discrete data cells or points, which will uh, connect the points and create your output. So the dependency on the discrete data set leads to this kind of shortcoming. Then there is a difficulty in dealing with the uncertainty. So in traditional GIS, data models may not explicitly represent uncertainty or provide robust methods for handling it, but in many of these advanced ones, you have this facility. It is not suitable for some types of data. There are certain types of data, such as the LiDAR point clouds or 3D models. These may not fit well into either raster or vector models without significant data transformation. So you might have to learn advanced data transformations to make it suitable for these types. Then you have complexity of data editing and maintenance. So what happens, even if you are trying to edit a complex vector data, especially in multi-user environments, it is going to be very challenging for you, and it will also require you to acquire some of the specialized tools and workflows. Even if I take a simple vector data as roads and imagine having a regional scale of your road network where there is so much redundancy. So even if you try to edit your complex vector data just for roads, okay, so roads is not having any multi-user environment. It does not require very specialized tools. Also, you can simply use the simplest form of editing tool in your vector data set, and you can continue with your editing. So if there are breaks in my road network and if I just want to fill them, this kind of simple editing or maintenance drive is also not possible, because I really wish there was a command where it could detect all the gaps in a single line and then fill it itself. There should be some command or some tool that could help me regenerate that in one click. But that is not possible. I have to manually go to each of the gaps and try to fill them. So this makes this process very hectic and very never ending time. So whether it is multi-user or not, irrespective of that, if you have any complex vector data and you're trying to edit it, it's going to be very hectic for you. So this is again another type of shortcoming. Then we have certain shortcomings in your entities and fields. So what happens, we experience this on a daily basis, that it is the area as an entity that carries the information. So in a real world model, we split the phenomena into two entities. Okay, so we have a real so what happens, let's say your real world is one specific entity that is not divisible into phenomena of the same kind, and this allows the entities to be bearers of information. For example, if my real world model has, let's say we are only talking about the water bodies. If it is very complex and if it is too high in number, what I'm going to do, I'm going to split it into two different entities. Let us say or maybe I will split it into three or four different entities. I will make a separate entity for my water bodies that are enclosed. I will make a separate entity for all my rivers. I'm going to make a separate entity for my canals, right? So I will make multiple entities if it is something complex. It is really challenging to make it in just one single entity, and this is again a type of drawback that comes with it, but then it has its own benefits also. Now, this model will allow an entity to represent only one phenomenon, right? So, what I did was I tried to break it up into different phenomena on the digital model. Although in the real world, all are associated with the water, but in the digital world, I have tried to break it into different phenomena. Then the challenge arises when we are trying to adapt the model to reality. There is overlapping of phenomena that are separated by layers. This reality is thus adapted to fit into a layer system that is used in map preparation. So there will always be interactive overlapping of interests that can be combated if there is some sort of advanced tools available in GIS, which as of now are not very user friendly and not actively being used. They have not been efficiently put out in the market, but we are hoping we will see them in future. I'm just getting a call which is really important. I will be back in 2 minutes. Please hang on. Yes, understood. हेलो दादा, मैं अभी क्लास में हूँ, आपको थोड़ा वेट करना पड़ेगा। मैं क्लास छोड़ के नहीं आ सकती हूँ। अब पता नहीं दादा, कल मेरा एग्ज़ाम ड्यूटी था। आप कल दे दीजिए, अगर अभी आप वेट नहीं कर पा रहे हैं तो कोई इशू नहीं है। ठीक है, ओके, थैंक यू। So let us talk about the uncertainty shortcomings. So here we are considering the physical world as comprised of geometric entities. So what are the geometric entities it is comprised of? That is points, lines and polygons or areas. And this entails in perceiving things as discrete representations inside a data model. So in other words, what we are doing here, uh, we are trying to possess well defined physical boundaries for all the objects that are present in the real world, and we are trying to digitally represent it in GIS. So what happens? The previously mentioned restrictions are particularly evident in cartography, where the representation of lines suggests distinct boundaries without gradual uninterrupted transitions. So the suitability of a discrete data model for representing reality is not always optimal due to challenges encountered in representing phenomena that lack distinct physical boundaries. For example, what are the soil typologies? These do not have any distinct boundaries. We try to define them with an uncertain boundary, right? Then we have a population density. We make a population density map, but those boundaries are very uncertain. They do not have a fixed physical boundaries. Then there is temperature variation, right? I hope you're able to understand the uncertainty shortcomings. So these are shortcomings, these are uncertainties, but still we use these maps to represent certain data because there is no other new or advanced methods known to do it. Then uncertainty may also arise in the determination of attribute values that are to be preserved. So similarly, for uh, parallel attribute values, you will have the same type of uncertainty. Then we have a conceptual generalization. What we are trying to define here is that the primary purpose of any GIS tool or any GIS assessment is to facilitate a rapid comprehension of information by recipients so that the ambiguity can be minimized. Now, the process of organizing and inputting information into the system is in a systematic manner to achieve this objective is referred to as data structuring or conceptual realization. So what we are doing is we take a real world model, we conceptually generalize it, we convert it into a data model, then we cartographically generalize it, and then we finally get our output map. So the aim of GIS here is to harness the power of geospatial information to improve our understanding of the real world so that we can effectively take decisions. The process of decision making can be smoothened, and this will contribute to a more sustainable and efficient practice in various domains. It plays a crucial role in fields as diverse as urban planning, environmental management, transportation, public health, and many more, which is already known to you. We have already spoken about it in the previous lectures. Then, if we consider these four diagrams, I'm sure you've seen it many times. So, here we are trying to show you that when points, lines, and polygons are selected as the geometric representation of the objects, this very often results in a generalization of the real world. So, what we are doing here is that we can represent a building by just a point rather than a polygon. And a road will be frequently represented by a center line and not two road verges. The need to divide the objects into classes also results in generalization. So, in general, the conceptual generalization is also a method for handling uncertain elements and further making in roads in uncertainty. So, this uncertainty can also be reduced by your conceptual generalization. So, it is important that you use this facility or this conceptual logic efficiently to reduce your uncertainties. Then we have a geographic phenomena. Geographic phenomena can be discrete in terms of your points, lines, and polygons. It can be continuous, which is represented by your terrain surface or mathematical surfaces. And then there is a fuzzy phenomena. So the difference between discrete and continuous is your fuzzy phenomena. What happens when you have a discrete phenomena? You are representing points, let's say cities and towers. If you are representing it with lines, it's roads or rivers. If you have polygons, it's forest water bodies. These are just some random examples. Then you have a continuous phenomena which has your elevational surfaces. Okay, so there is a 3D involved in it. So this fuzzy phenomena is a diffusion of your discrete and continuous. The phenomena which is between these two is your fuzzy phenomena. Now, how do you consider maps when you're doing data modeling? This is very simple. At the same time, if you want to talk about it in a bookish language, it becomes little prevalent and difficult. So, maps in general, we consider them to be reliable sources for describing anything and for including certain properties. In terms of GIS, we are using it to represent certain spatial and attribute properties. But it is also crucial to acknowledge that maps inherently include certain conceptualizations of reality, while GIS should strive to accurately reflect the actual world rather than being limited to the subjective nature of maps. But maps help us represent the actual world through GIS. So, for example, if you have certain cartographic representations, often used dotted lines to depict ferry routes. Okay, this is just an example. However, in the context of transportation planning, the data model should be seamlessly integrated into a connected road network. The dots are actually not going to work in that case, but they will help you for the ferry routes. Correct? In the light of conventional wisdom, it is advisable to see a map primarily as the source of data rather than as a model of the data. So this is just a map representation. So it's not possible to move this right now, but since I was looking at on a certain website, so you could actually scroll this and see the change in temperature in different parts. So if I would scroll this, I will actually see a temperature change in different in different seasons of this particular geographic location, right? So map plays a very important and crucial role, but cartographically those representations should be used as efficiently as possible. So it's very important that you give the correct symbology, you give the correct labels, you use the correct cartographic representations. For example, this legend is also a cartographic representation, but this map lacks scale and north pointers. Okay, it also lacks a master map or a key map. Extension of reality concepts. So in traditional models, we describe flats and unchanging reality. Then we have elevation values that can be linked to features, thereby giving the object's position in the space. For example, the surface of the terrain can be represented as sloping areas. So it is giving it a 3D vibe. It is giving it a 3D attribute value. Elevation values can also be linked to above ground objects such as towers, buildings, and wells. Right? So wells are not exactly above the ground object. Well will actually come into below the ground object. So you're going in depth, not in height. So we finally come to the summary of this session. So we have tried to understand how object relations are, what are their types, then the certain outcome shortcomings of your GIS models, especially in terms of your entities and fields, then the types of geographic phenomena, that is your discrete, continuous, and fuzzy, the uncertainty in your data models, how you can actually reduce the uncertainty because you definitely cannot get rid of them, then generalization phenomena, which is again very important. For the next class, we will be talking about the GIS data and their types. I hope this session was a little bit useful to you and you've got some little extra information related to this lecture and this specific module. I thank you all for your attention. If you have any questions, you may ask. Okay, so I will be closing this session. Thank you all. I will see you next week in lecture 9. Good night,